Welcome to the deep dive. You've likely felt that subtle pressure change when a weather front moves in, maybe.
Oh, absolutely. Or even just pumping up a bike tire, right? You feel that resistance building.
Exactly. Gases are just, well, they're everywhere. Invisible, but incredibly powerful. They drive everything from, the breath you're taking right now to how a plane stays up.
And it's fascinating because these aren't just random things happening. There are fundamental principles behind it all. For anyone who's already got the basics down, our mission today is really to cut through some of the, let's say, textbook density.
Yeah, get straight to the point.
Right. We want to focus on the deeper insights, the real-world connections, and give you a kind of sharp, engaging shortcut to a more expert-level understanding.
Right, like that expert shortcut. So today, we're diving into Chapter 5 of Chemistry, the Molecular Nature of Matter and Change by Silverberg and Amatis. We're aiming for those aha moments about gases. We'll start with what makes gases unique compared to liquids and solids, then explore the foundational laws, see how they play out in the real world, and finally, unpack the kinetic-molecular theory that explains the why behind it all.
And we'll even touch on how real gases sometimes, well, deviate a bit from the ideal picture.
Okay, let's start there. Gases fill their containers completely. We know that. But why? What gives them that sort of freedom compared to, say, water or a block of wood?
It really boils down to two things. The particles themselves are incredibly far apart. There's just vast empty space between them. And second, they're in constant, completely random motion, bouncing all over the place.
That makes sense. And that basic structure leads to some really distinct properties, doesn't it?
Absolutely. Properties that are starkly different. Take compressibility. You can squeeze a gas, force those particles much closer together. Think about compressed air in a jackhammer just shattering rock.
Or just the air in your car tires holding up the weight of the car.
Exactly. Liquids and solids, they're already packed tight. You can barely compress them at all. It's a huge difference.
And it's not just pressure.
Yeah.
Temperature has a massive effect too, right? Thermal expansion.
Oh, huge. Thermal expansion in gases is dramatic. Heat a gas, and its volume can balloon out maybe 50 to 100 times more than a liquid or solid would for the same temperature increase.
Like popcorn. That sudden burst is gas expanding.
Precisely. Or think bigger, like the expanding gas is lifting a rocket off the launch pad. It's the same principle.
And then there's how easily they flow.
Yeah, free flow. Much more freely than liquids. Makes them easy to transport in pipes, but also means leaks can happen fast.
That are not very dense.
Not at all. Low densities. About 1,000 times lower than liquids or solids. We measure gas density in grams per liter, while liquids are grams per milliliter. That's why helium balloons float, right? Helium is much less dense than air.
Okay, and the last one, solution formation.
Right. Gases form solutions mixtures in any proportion. Air is a perfect example. It's a solution of, 18 or so gases all mixed together perfectly. Liquids might mix, or they might not. Solids rarely do homogeneously.
So these 5 things, compressibility, thermal expansion, flow, low density, and mixing, really set gases apart.
They do, and understanding them is key to everything from weather forecasting to chemical engineering.
Okay, so let's talk pressure. We feel atmospheric pressure, we inflate tires, but what is pressure at that tiny particle level?
Pressure is fundamentally about collisions. It's the result of all those gas particles moving randomly at high speeds, constantly smacking into the walls of whatever container they're in.
Billions and billions of tiny impacts.
Billions upon billions, yeah. Each single collision exerts a tiny force, but add them all up over the surface area, and you get the macroscopic pressure we measure. Force per unit area. That's why you can inflate a balloon, the internal pressure pushes outwards.
It's amazing that all that random motion creates such a steady, measurable force. And how do we measure it accurately? I know barometers are key.
Right. The barometer, invented by Torricelli way back in 1643. It was a genius setup. He filled a tube with mercury, inverted it into a dish of mercury, and saw that not all of it flowed out.
Why mercury?
Because it's incredibly dense, about 13.6 times denser than water. This meant his barometer only needed to be, a manageable height. At sea level, the column of mercury that the atmosphere could support was about 760 millimeters high.
And if you'd use water?
It would have needed to be over 34 feet tall. Impractical. But the key insight, as Galileo hinted, was that the atmosphere was pushing the mercury up into the tube. It wasn't a vacuum sucking it up.
And the width of the tube doesn't matter, just the height supported by the atmosphere.
Exactly. Counterintuitive? Maybe, but
Yeah.
true. Now, in the lab, we often use manometers. Usually a U-shaped tube with a liquid, often mercury again.
How do those work?
Well, a closed-end manometer measures the gas pressure directly by the height difference in the two arms. An open-end one compares the gas pressure to the atmospheric pressure, so you'd need a barometer reading too. It's the same basic principle behind a blood pressure cuff, actually.
So we have ways to measure it. What about units? I see atmospheres, pascals, torr.
Yeah, there are a few common ones. The official SI unit is the pascal, para, which is 1 Newton per square meter, but it's quite small, so we often use kilopascals, kPa.
But IRM is common too.
Very. The standard atmosphere, Edo, is defined as the average pressure at sea level, and then there's millimeters of mercury, mmHg, directly from the barometer reading. That unit was renamed the torr in honor of Torricelli. So 1 torr equals 1 mmHg.
Okay, so how do they relate?
The key conversion is 1 atom m at 760 mmHg of 760 torr equals 101,325 tau, or 101.325 kPa. Knowing these is essential for any kind of calculation or data comparison.
Got it. So we understand gases have unique properties, and we can measure their pressure. Now, how do pressure P, volume V, temperature T, and the amount of gas, N, in moles, all relate to each other?
Now we get to the core gas laws. These 4 variables are interdependent. If you know 3, you can determine the 4th. And for many common gases, like nitrogen, oxygen, hydrogen, the noble gases, under sort of ordinary conditions.
Like room temperature and pressure.
Exactly. They behave very predictably, almost ideally. Their relationships are quite linear.
And these relationships were discovered through experiments, right? Like Boyle's law.
Precisely. Boyle's law came first. Robert Boyle found that if you keep the temperature and amount of gas constant, the volume is inversely proportional to the pressure. Squeeze it harder, the volume gets smaller. Mathematically, PV equals some constant value.
He used that J-shaped tube experiment, trapping air with mercury.
That's the one. Adding more mercury increased the pressure on the trapped air, and he saw the volume decrease proportionally. Double the pressure, halve the volume. Simple but profound.
Then came Charles. What did Jacques Charles figure out?
Charles's law looked at volume and temperature, keeping pressure and amount constant. He found that volume is directly proportional to the absolute temperature.
Absolute temperature, meaning Kelvin.
Yes, absolutely crucial. You must use the Kelvin scale, Celsius plus 273.15. If you double the Kelvin temperature, you double the volume, assuming pressure doesn't change.
And this points towards absolute zero.
It does. If you extrapolate the volume temperature graph backwards, it hits zero volume at 273.15 degrees C, which is 0 Kelvin. Of course, a gas would liquefy before then, but theoretically, that's absolute zero.
Okay, Boyle is P and V, Charles is V and T. What about P and T?
That's often called Amonton's law, though sometimes credited to Gay-Lussac too. It states that if you keep the volume and amount of gas constant, the pressure is directly proportional to the absolute temperature.
Like my car tires getting higher pressure on a hot day or after driving.
Exactly that. The temperature increases from friction and the road, particles move faster, hit the tire walls harder, and more often, pressure goes up.
Makes sense. And the last piece of the puzzle involves the amount of gas.
Right, Avogadro's law. Amedeo Avogadro proposed that if you keep temperature and pressure constant, the volume of a gas is directly proportional to the number of moles, the amount of gas. Add more gas, the volume increases.
So double the moles, double the volume.
Under the same T and P, yes. This leads to a really key insight. Equal volumes of any ideal gases at the same temperature and pressure contain the same number of particles or moles. Doesn't matter if it's helium or oxygen or methane.
That's quite a statement. And this ties into STP, standard temperature and pressure.
It does. STP provides a reference point. It's defined as exactly 0 degrees C, which is 273.15 K, and 1 at Lenum, or 760 torr.
And at STP, what's the volume of 1 mole of gas?
At STP, 1 mole of any ideal gas occupies a volume of 22.414 liters. We often round it to 22.4 liters. It's called the standard molar volume.
22.4 liters. Hard to picture.
Think of maybe a basketball and a half, or about 6-gallon jugs of milk. It's a useful benchmark.
Okay, so we have Boyle, Charles, Amonton's, Avogadro, relating P, VT, and N in pairs. Is there a way to put it all together?
There is, and it's incredibly elegant. It's the ideal gas law. PV equals nRT.
The famous one.
The famous one. It combines all those individual relationships into a single equation. P is pressure, V is volume, N is moles, T is absolute temperature in Kelvin, R is the universal gas constant. Its value depends on the units you use for P and V, but the most common one is 0.0821 atmosphere liters per mole Kelvin at mmHg.
And why is this law so powerful?
Because if you hold certain variables constant, it simplifies back to the individual laws. For example, hold T and N constant. PV equals constant. That's Boyle's law. Hold P and N constant, VT equals constant Charles's law. You don't need to memorize all four if you understand PV and RT.
That is clever. And these laws aren't just equations. They describe real things happening all the time.
Constantly. Think about breathing. You expand your lungs, increase V, pressure inside drops, Boyle's law, so air flows in. That air contains moles of gas, Avogadro's. It warms up in your lungs and expands slightly, Charles's. Exhaling reverses it.
Or baking bread.
Right. Yeast makes CO2 gas bubbles, Avogadro's. You put the dough in a hot oven, those bubbles expand dramatically, Charles's, making the bread brine.
Hydrogens, explosions.
Same ideas. Chemical reactions produce a large number of moles of hot gas, Avogadro's, Charles's, rapidly increasing pressure and volume, creating force. It's fundamental.
Wow. Okay, so PV and RT is central. Can we rearrange it to find other useful things?
Absolutely. It's very versatile. One common application is calculating gas density. Remember, density is mass per unit volume, D equals mV.
And moles N is mass M divided by molar mass M, right? NMMM.
Exactly. So substitute NMM into PV nRT. You get PV nRT, you get PV mmRT. Rearrange that to get mV, which is density. You find that D and a mRT.
So gas density depends on pressure, molar mass, and temperature.
Directly proportional to pressure and molar mass, but inversely proportional to temperature. Higher pressure or heavier molecules mean denser gas. Higher temperature means less dense gas.
And this has real consequences.
Huge ones. Why are heating vents near the floor? Because hot air is less dense and rises, Charles's law in action. Why do CO2 fire extinguishers work? CO2 is much denser than air, higher molar mass, so it sinks onto the fire and displaces the oxygen.
That density factor was also behind some tragedies, wasn't it?
Sadly, yes. Toxic gases used in warfare, like phosgene, or industrial accidents like Bhopal involving methyl isocyanate, were devastating, partly because the gases were denser than air and stayed near the ground. The Lake Nyos CO2 disaster, too dense, CO2 flowed downhill.
But on the flip side, heating air makes it less dense.
Which is how hot air balloons work. Heat the air inside, it expands, becomes less dense than the surrounding cooler air, and creates lift. It's all D equals PMRT.
Okay, besides density, what else can we get from rearranging PV and RT?
We can find the molar mass of an unknown gas or even a volatile liquid. If you rearrange PV and RT to solve for M using NMM, you get mmRT PV.
So if I measure the mass, volume, pressure, and temperature of an unknown gas sample,
You can calculate its molar mass. Chemists do this by vaporizing a liquid sample in a flask of known volume, measuring T and P, and weighing the condensed liquid. A classic experiment.
cool. What about mixtures of gases, like air?
That's where Dalton's law of partial pressures comes in. John Dalton stated that in a mixture of gases that don't react with each other, each gas behaves as if it's alone in the container.
Meaning each gas exerts its own pressure.
Exactly, its own partial pressure. And the total pressure of the mixture is simply the sum of all those individual partial pressures. P total equals P1 plus P2 plus P3, and so on.
How do we figure out the partial pressure of just one gas in the mix?
We use the mole fraction, X. That's the number of moles of one specific gas divided by the total number of moles of all gases in the mixture. The partial pressure of gas, PA, is just its mole fraction, XX, times the total pressure, P total. PA is XA total.
Practically use this.
Oh, yeah. Physiologists studying oxygen uptake at high altitude might create special gas mixtures with precisely controlled partial pressures of oxygen and nitrogen to simulate conditions.
Okay, I remember doing experiments where we collected gas over water. How does Dalton's law apply there?
Collecting gas over water, a common lab technique. When you do that, some water evaporates and mixes with the gas you're collecting.
So the total pressure you measure includes water vapor.
Yes. The water vapor exerts its own partial pressure, called the vapor pressure of water. And this vapor pressure depends only on the temperature of the water.
So how do you find the pressure of just the dry gas you collected?
You look up the vapor pressure of water, pH2O, at the experimental temperature in a table, and then you just subtract it from the total measured pressure. P gas equals total pH2O. Simple application of Dalton's law.
Makes sense. And one more application of the ideal gas law, stoichiometry.
Definitely. Gas stoichiometry. Since PV and RT links P, V, and T directly to the amount of gas and moles, we can use it in stoichiometry calculations involving gas reactants or products.
So you could calculate, say, how many liters of CO2 gas are produced from burning a certain mass of methane at a given temperature and pressure.
Precisely. Or figure out how much lithium hydroxide is needed to remove the CO2 exhaled by astronauts in a spacecraft, based on the volume of CO2 produced. It connects the gas laws directly to chemical reactions.
Okay, we've covered the what and the how, the properties, the laws, the ideal gas law, its applications. Now, the why, the kinetic molecular theory. KMT. This explains why gases behave this way, right, on a particle level.
Exactly. KMT is a model that explains the macroscopic gas laws by describing the behavior of individual gas particles, atoms, or molecules.
What are the main ideas?
There are three key postulates. First, particle volume. Gas particles are tiny, and the space between them is enormous compared to the size of the particles themselves. So we assume the particle volume is essentially negligible, zero.
An idealization, but okay.
Second, particle motion. The particles are in constant random straight line motion until they collide with other particles or the container walls.
Like tiny billiard balls zipping around.
Oh. Kind of, yeah. And third, particle collisions. These collisions are perfectly elastic. That means the total kinetic energy, energy of motion, is conserved during collisions. They don't lose energy overall. Also, critically, we assume there are no attractive or repulsive forces between the ideal gas particles.
No sticking together, no pushing apart. Another idealization.
A very important one for the ideal model. Now, these particles don't all move at the same speed. There's a distribution of speeds.
But there's an average.
Yes, and here's the absolute crucial insight from KMT. The average kinetic energy of the gas particles is directly proportional to the absolute temperature in Kelvin.
Take T.
So temperature is just a measure of that average kinetic energy.
That's exactly what temperature is on a molecular level. Higher temperature means, on average, the particles are moving faster and have higher kinetic energy.
And this average kinetic energy is the same for all gases at the same temperature, even if they have different masses. Yes, at a given temperature, helium atoms and, say, much heavier xenon atoms will have the same average kinetic energy. The lighter helium atoms just have to move much, much faster to make up for their smaller mass, since EK equals 12 mass velocity 2.
Wow, okay. So how does this particle view explain the gas laws we talked about? Pressure.
Pressure comes directly from those countless elastic collisions of particles with the container walls. More collisions or harder collisions mean higher pressure.
Boyle's law, V1P.
If you decrease the volume, the particles have less distance to travel before hitting a wall. They hit the walls more frequently. More collisions per second means higher pressure. Simple.
Why aren't liquids and solids compressible then?
Because their particles are already touching, essentially. There's no significant empty space to reduce.
Dalton's law, P total if P1 plus P2 plus.
If particles don't interact, ideal assumption, adding more particles just increases the total number of collisions with the walls, regardless of what kind of particle they are. Each type contributes to the total pressure based on how many particles of that type there are.
Charles's law, VT.
Increase the temperature, the particles gain kinetic energy, move faster, they hit the walls harder and more often. This increases the internal pressure. If the container can expand, like a balloon or piston, it will push outwards until the internal pressure equals the external pressure again, resulting in a larger volume.
In Avogadro's law, V-ene.
Add more moles, more particles at constant T and P. More particles mean more wall collisions, temporarily increasing pressure. Again, the container expands to bring the pressure back down to match the external pressure, resulting in a larger volume.
And it explains why equal moles of light H2 and heavy O2 occupy the same volume at the same T and P.
Yes, the light H2 molecules move much faster, hitting the walls more often. The heavy O2 molecules move slower but hit with more force per collision, more momentum. These two effects balance out perfectly so that the average force exerted on the walls, pressure, is the same if you have the same number of moles at the same temperature. It's a beautiful balance.
That really connects the micro and macro. What about things like smelling perfume across a room? That's diffusion, right?
Right. KMT also explains diffusion, the mixing of gases, and effusion, a gas escaping through a tiny pinhole into a vacuum.
And there's a law for that too.
Graham's law of effusion. Thomas Graham found that the rate at which a gas effuses is inversely proportional to the square root of its molar mass. Rate 1 urim.
So lighter gases effuse faster.
Much faster. Helium, M4 gyrum, effuses 4x times faster than methane, M16 gyrum, because SUF4 equals 2.
But if gas molecules move so fast, hundreds of meters per second, why does it take time to smell perfume? Diffusion seems slower than effusion into a vacuum.
Great question. It's because diffusion happens through other gas molecules, like air. The perfume molecule travels a very short distance before colliding with an air molecule, changing direction, hitting another, and so on. It's a very zigzag path.
So it has a short mean free path.
Exactly. The mean free path is the average distance a particle travels between collisions. For nitrogen at STP, it's only about 60 nanometers, maybe 180 times its own diameter. Tiny distance.
And they must be colliding incredibly often.
Mind-bogglingly often. The collision frequency for that nitrogen molecule at STP is around 7 billion collisions per second. 7 by 109.
That's insane, like molecular bumper cars on overdrive.
It really is an incredibly chaotic, high-energy environment at the molecular level.
Does KMT help explain the atmosphere too? Like pressure changes with altitude?
It does. Atmospheric pressure decreases smoothly as you go up because there's less air mass pressing down from above. Gases are compressible, Boyle's law again, so most of the atmosphere's mass is packed closer to the surface.
But temperature's more complex, right? That zigzag pattern.
Yes, temperature doesn't change smoothly. In the troposphere, where we live, up to about 17 kilometers, temperature drops with altitude. This layer has 80% of the atmospheric mass and all the weather.
And then it warms up.
In the stratosphere, up to 50 kilometers, yes, temperature increases because this is where ozone, O3, is formed. The process of ozone formation absorbs high-energy UV radiation from the sun and releases heat. That ozone layer is vital, blocking most harmful UV.
Then it drops again.
In the mesosphere, temperature falls again. Then way up in the thermosphere and exosphere, it rises dramatically, maybe to 700, 2000 K, because the few particles up there absorb intense solar radiation.
But 2000 K doesn't mean it feels hot up there.
Right. Temperature is average kinetic energy, but hotness is about energy transfer. The density is so incredibly low up there, particles rarely collide with you to transfer that energy. You'd freeze before you felt hot.
And how does convection fit in? The air mixing.
That's driven by solar heating at the surface. Air warms, expands, Charles's law, becomes less dense, and rises. As it rises, the surrounding pressure drops, so it expands more, Boyle's law, and cools. Water vapor might condense, releasing heat which helps it keep rising. Meanwhile, cooler, denser air sinks elsewhere. This constant vertical mixing keeps the composition of the lower atmosphere relatively uniform.
Explains weather patterns, pollutant dispersal.
Wow. Okay, so KMT and the ideal gas law are incredibly useful, but you mentioned deviations. Real gases aren't perfectly ideal.
They aren't. The ideal model is fantastic, but it relies on those two simplifying assumptions.
Yeah.
Negligible particle volume and no intermolecular forces. Neither is perfectly true for real gases.
And these assumptions break down under certain conditions.
They become noticeable, especially at low temperatures and high pressures.
Well, at low temperatures, particles move slower, so any weak attractive forces between them have more time to act. They stick together slightly. At high pressures, the particles are forced much closer together, so the actual volume they occupy becomes a significant fraction of the total container volume.
So the two postulates start to fail. How does this show up in measurements?
We often look at the ratio PVRT for 1 mole of gas. For an ideal gas, PVRT should always equal 1. For real gases, it deviates.
How do they deviate?
There are two competing effects. At moderately high pressures, those interparticle attractions become important. They pull particles slightly away from hitting the walls as hard, or towards each other, reducing the effective pressure. This makes the measured PVRT ratio less than 1.
Attractions lower the pressure. What about the particle volume?
At very high pressures, the particle volume effect dominates. The actual free space the particles have to move in is less than the total container volume, V, because the particles themselves take up space. Using the full V in PVRT makes the calculated ratio greater than 1.
So attractions pull PVRT below 1. Particle volume pushes it above 1.
Generally, yes. For many gases like methane or CO2, you see PVRT dip below 1 first as pressure increases, attractions win, then rise above 1 at very high pressures, volume wins. For gases with very weak attractions, like hydrogen and helium, the volume effect dominates almost immediately, so PVRT stays above 1.
So we need a better equation for real gases under these conditions.
Johannes van der Waals came up with one. The van der Waals equation adjusts the ideal gas law to account for these two factors. It looks like P plus NAEV equals nRT.
Whoa, okay. What are A and B?
They are constants specific to each gas. The A term corrects the measured pressure upwards to account for the reduction caused by interparticle attractions. The B term, MB, corrects the container volume downwards by subtracting the volume actually occupied by the gas particles themselves.
So A deals with attractions, B deals with particle size.
Essentially, yes. For an ideal gas, A and B would be 0, and you'd just get PV nRT back. But for real gases, especially under extreme conditions, these corrections make a big difference.
How much difference?
It can be significant. Under some conditions where the ideal gas law might be off by, say, 35%, the van der Waals equation might only be off by 2 or 3%. It's a much better description of reality when ideality breaks down.
That really shows how science works, doesn't it? Start with a simple model, see where it fails, and then refine it.
Precisely. The ideal gas law is powerful because it's simple and works well most of the time. The van der Waals equation adds complexity but gains accuracy where needed.
Okay, wow. We've really covered a lot of ground.
Yeah.
From just observing that gases fill space to understanding their unique properties like compressibility and low density.
To the fundamental gas laws, Boyle, Charles, Avogadro, and how they all come together in the elegant ideal gas law, PV-nRT.
We saw how rearranging that one equation lets us calculate density and molar mass, understand partial pressures with Dalton's law, and even tackle stoichiometry for gas reactions.
Then we dove into the why with the kinetic-molecular theory, visualizing gases as tiny particles in constant chaotic motion, where temperature is just a measure of their average kinetic energy.
Explaining everything from pressure and diffusion to the structure of our atmosphere based on that particle behavior, it's quite amazing.
And finally, acknowledging that our models have limits, and real gases deviate from ideal behavior due to particle volume and attractions, leading to refinements like the van der Waals equation.
It really shows how something seemingly simple, the behavior of gases, unlocks these really deep insights into matter, energy, and how the world works.
It truly does. These principles are operating constantly all around us.
So as you go about your day, maybe think about that. The air you're breathing, the pressure in a soda can before you open it, the weather forecast.
Yeah.
It's all governed by these ideas. And maybe ask yourself, what other everyday things could be explained by these principles if you just, unpack them a bit more?
And how might understanding the limits of these models, where they start to break down, inspire new questions? What happens at even more extreme conditions or with more complex molecules?
Always more to explore. Thank you for diving deep with us today on the behavior of gases.
It was a pleasure. Keep asking those questions.
Keep exploring and keep learning.